Imagine a Tuesday morning where every digital vault on Earth simultaneously swings open. Trillions of dollars in global markets, classified military communications, the biometric data of billions of citizens, and the proprietary secrets of every major technology corporation are suddenly laid bare, stripped of the cryptographic armor that has protected the modern internet for decades. This is not a speculative cyber attack, but the mathematical inevitability of the quantum age. Traditional encryption relies on mathematical problems that take classical computers millennia to solve, but a sufficiently powerful quantum computer could unravel them in mere seconds. To prevent this digital apocalypse, humanity is racing to build a successor to our current network. We are attempting to construct a secure quantum internet. This new paradigm discards the classical bits of ones and zeros that currently pulse through our fiber optic cables. Instead, it relies on the baffling laws of subatomic physics, specifically a phenomenon known as quantum entanglement. Entanglement occurs when two particles become intrinsically linked, such that the state of one instantly influences the state of the other, regardless of the physical distance separating them. Albert Einstein famously derided this as spooky action at a distance. Yet it is the foundational bedrock upon which the unhackable communication networks of tomorrow are currently being engineered. The implications of harnessing this spooky action are profound. A mature quantum internet would not merely upgrade our download speeds or bandwidth, it would fundamentally alter the geometry of digital trust. In a world where data is the most valuable commodity, the ability to transmit information with absolute physics-mandated security shifts the balance of global power. Financial institutions could execute trades immune to interception, while sovereign nations could coordinate defense strategies completely insulated from foreign espionage. The race to achieve this is the defining geopolitical and technological contest of the 21st century. Explaining the ultimate security of this network requires examining the specific protocol at its heart, known as quantum key distribution, or QKD. QKD is a method for two parties to generate a shared, secret cryptographic key using entangled photons. The sender encodes information into the physical properties of these tiny packets of light, such as their polarization. The brilliance of QKD lies in another fundamental quirk of quantum mechanics. The act of observing a quantum system inevitably alters its state. If a malicious actor attempts to intercept or eavesdrop on the transmission of these entangled photons, the delicate quantum state collapses immediately. This collapse leaves a distinct, measurable footprint on the transmission itself. The legitimate communicating parties instantly detect the disturbance, alerting them that the channel has been compromised before any sensitive data is actually transmitted. They simply discard the corrupted key and generate a new one. It is a security system guaranteed not by the complexity of a mathematical algorithm, but by the immutable laws of the universe itself. Eavesdropping becomes physically impossible to hide, rendering the communication truly unhackable. The theoretical elegance of QKD was dramatically proven on a global scale in 2016 when researchers in China launched the Messias satellite. Orbiting 500 kilometers above the Earth and traveling at immense speeds, Messias successfully beamed entangled photons to two ground stations separated by over 1,200 kilometers. Navigating atmospheric turbulence and light pollution, this monumental achievement shattered previous distance records for quantum communication, proving that entanglement could survive the chaotic journey through the Earth's atmosphere. The success of the Messias satellite sent a shockwave through Western intelligence agencies and the global scientific community. It demonstrated that the theoretical physics of the quantum realm could be weaponized for strategic advantage in the vacuum of space. The satellite was not just a scientific curiosity, it was a glaring signal that the infrastructure for a fundamentally new global network was already being deployed. The era of quantum supremacy in communication had quietly begun, sparking a frantic race to catch up. Yet, beaming photons through the empty vacuum of space is vastly different from threading them through the terrestrial fiber optic networks that form the backbone of the current internet. Here, engineers face their most punishing adversary: decoherence. Quantum states are extraordinarily fragile. When a photon travels through standard silica glass fiber, it inevitably interacts with the material, losing its quantum information. The photon might be absorbed by an impurity in the glass, or its delicate quantum state might be scrambled by microscopic temperature fluctuations. After just a few dozen kilometers, the signal degrades entirely, swallowed by the noise of the environment. In classical computing, this signal loss is solved by installing amplifiers at regular intervals along the cable to boost the signal. However, the quantum realm strictly forbids this approach. A fundamental principle of quantum mechanics, known as the no-cloning theorem, dictates that it is impossible to create an identical copy of an unknown quantum state. If you cannot copy the photon, you cannot amplify it. This paradox represents the single greatest engineering bottleneck in the creation of a terrestrial quantum internet. To bypass the no-cloning theorem, physicists are attempting to build quantum repeaters, devices that operate on entirely different principles than their classical counterparts. Instead of amplifying a signal, a quantum repeater utilizes a mind-bending process called entanglement swapping. Imagine three nodes in a network, A, B, and C. Node A shares an entangled pair with node B, and node B shares a separate entangled pair with node C. By performing a specific measurement at the central node B, engineers can force node A and node C to become entangled with each other, even though they have never directly interacted. Executing entanglement swapping in a sterile laboratory is difficult enough, but engineering it for a rugged, real-world network is a nightmare of precision. These repeaters require quantum memory to briefly store the fragile state of a photon while the swapping operation occurs. The materials required to build this memory are exotic and highly temperamental. Researchers are experimenting with ultra-cold atomic gases, trapped ions suspended in electromagnetic fields, and even microscopic defects engineered into synthetic diamonds. Each of these memory substrates demands extreme operational conditions. To prevent the ambient heat of the environment from destroying the quantum information, these memory nodes must often be cooled to temperatures approaching absolute zero, colder than the deepest voids of interstellar space. This requires massive, energy-intensive dilution refrigerators running constantly. Engineering a global network that requires thousands of these cryogenic, hypersensitive nodes to operate continuously, without failure, across continents and ocean floors, is a logistical challenge that dwarfs the construction of the original Internet. If these monumental engineering hurdles can be cleared, the resulting infrastructure will facilitate technologies that currently sound like science fiction. Beyond unparalleled security, a fully realized quantum internet will enable blind quantum computing. This protocol allows a user to access a remote quantum supercomputer and run complex algorithms without the computer itself ever knowing what data it is processing or what the results mean. The privacy of the user is mathematically guaranteed, opening the door for secure, cloud-based quantum processing for medical research and advanced material science. Furthermore, this network will connect distributed arrays of quantum sensors, creating a telescope of unprecedented resolution or a geological monitoring system capable of detecting the most minute shifts in tectonic plates. The entanglement of sensors across vast distances will effectively create a single Earth-sized instrument, fundamentally transforming our ability to measure and understand the physical world. The quantum internet is not merely a communication tool, it is a new nervous system for human civilization. However, the deployment of such a powerful infrastructure raises profound ethical and geopolitical dilemmas. The immense cost and specialized knowledge required to build this network mean it will likely be monopolized by a handful of technological superpowers and elite corporations. We risk creating a bifurcated world, divided into quantum haves and have-nots. Those with access to the network will operate behind an impenetrable shield of perfect security, while the rest of humanity remains vulnerable on the legacy internet, exposed to the predatory algorithms of classical cyber warfare. The ghost of those initial ethical debates will linger as the first commercial nodes eventually come online. The transition will not be a sudden flip of a switch, but a gradual, agonizingly complex integration. Hybrid networks will emerge where classical data is encrypted using quantum keys, bridging the gap between the old world and the new. This transitional phase will be fraught with vulnerabilities, as adversaries exploit the seams where classical architecture meets quantum protocols. Securing these hybrid seams requires the development of post-quantum cryptography, mathematical algorithms designed to be resistant to quantum attacks. These algorithms rely on entirely new mathematical foundations, such as lattice-based cryptography, serving as a stopgap while the physical quantum infrastructure is laid down. Yet mathematicians acknowledge that these classical algorithms are only temporary shields. True, permanent security can only be achieved by completing the physical quantum network, turning the very fabric of space-time into the ultimate cryptographic vault. The laboratories pushing this frontier are already achieving staggering milestones. Researchers are successfully miniaturizing quantum components, shrinking room-sized optical tables down to integrated photonic chips that can be mass-produced using the same fabrication techniques that build our current smartphone processors. These chips guide single photons through microscopic silicon channels, executing complex quantum logic gates with vanishingly small error rates. The hardware is slowly migrating from the realm of bespoke physics experiments to the domain of scalable, solid-state engineering. As these chips integrate into our global infrastructure, the very concept of digital privacy will be rewritten. We are standing at the precipice of a structural evolution in how humanity shares and protects its collective knowledge. The engineering challenges are monumental, requiring a synthesis of theoretical physics, material science, and cryogenic engineering that pushes the absolute boundaries of human ingenuity. The secure quantum internet is the ultimate moonshot of our digital era. It is a testament to our relentless drive to master the deepest, most counterintuitive laws of nature. When the final entangled link is established and a perfectly secure transmission spans the globe, we will not have just upgraded our communication networks. We will have fundamentally altered our relationship with information, securing humanity's digital legacy within the unbreakable laws of the quantum realm.